And there we go. All right. So once the recorder is going, we'll first go take a look at a C program, that explains to remind you what a structure is in C. And well, I mean, some people might have not programmed in C with structures for some time. I know some of you are in C++, object-oriented programming, or have taken data structure already, so you already know your structures well. But assuming that people may not have done that, this is just a quick reminder of what structures are. Okay, so we'll just go ahead and write a very simple program. Okay, so we'll just call this struct1.c to illustrate what a structure is. So in C, the way you define a structure is like this. Just start with the word struct. You can name a struct if you want to. Okay, you don't have to. Sometimes people create unnamed structures, just the variables. Because all you can do, you can do a struct. You can just say x, y as individual members, and then you have a char array. A bracket 20, and instead of giving a name, you can just create these particular structures A and B. So in this case, A and B are global variables of that particular type. But that type is not named at all. So you can do things about A and B and also its members, but you cannot create any additional objects or variables of that kind because it doesn't have a name. So what we usually do is we give a structure a name, and this is kind of like a convention. When you create the name, when you name a structure, it's just like when you name a class, you start with uppercase letters. Is that how you guys do things in your C++ class too? When you define a new class, you start with a name that has an uppercase letter?
Depends on the instructor.
Depends on the instructor? Really? Okay, well, it's a convention, okay? So the compiler does not enforce that particular standard, but as far as I know, this is a convention used in not only C and C++, but also in Java, PHP, Perl, and anything that is remotely capable of object-oriented programming. Okay, so we'll follow that convention in this class and use uppercase as the name of structures. Okay, so here is a structure, and I can create variables of that structure in a particular subroutine. So I can say we got main, okay, and then we'll go ahead and create one of these things. So we'll just say struct x, and then we have my variable. I'll just call it var1, okay, which is my variable. All right, so here is a little reminder for people who have been programming in C++ for a long time. In C++, if you say class x and then use the rest of the definition, when you want to create a variable, you just say x var1. Okay, you don't say class x var1. But in C, in regular C, you do have to say struct x and then the name of the variable that you're trying to create. Minor syntax differences, but nonetheless it is there. Okay. So I'm creating a variable called x here, and what I want to do is to find out from the beginning of the entire structure var1, what are the byte offsets into each individual member. That's what I want to find out. Okay, where is x, where is y, and where is a within a structure? So the first thing we have to kind of understand, which is kind of implicit, is within a particular structure, everything is contiguous. In other words, you cannot have members of two different structures interleaved. I mean, that just doesn't make sense, right? Okay. So how do I find out those offsets? Well, we're going to use printf for that purpose. Okay. So we'll include stdio, printf, and in this case, I'm going to change this program a few times. So the first one, I'll just say offset to member x is this many bytes. I'm just going to use %d to print a unsigned integer, and you can now see how GDB got its the code for the types from. It's all from printf. Okay, d is unsigned integer decimal, and then u is for unsigned decimal. Unsigned integer decimal, x for hexadecimal, and so on. Okay. So how do I do this calculation? Well, the first thing that most people think is, oh, okay, we'll just go ahead and look at the var1, the address of var1 dot x, okay, which is the member x, the address of member x of var1, and we'll just subtract it from the address of var1. That should give me the offset to member x in the variable of var1, not var, okay? Well, we have a few problems here. Even though in concept it seems to work because we are just subtracting an address from another address, it doesn't work. That's because C and C++, or C in this case, is strongly typed. In other words, not only is var1 itself typed, the pointer of that is also typed. Now, when you subtract a typed address from another typed address, they have to be of the same type. That's the first problem. And then the second problem is with arithmetic, with pointers, it doesn't give you the actual distance in number of bytes. It gives you the number of objects of that type in terms of, and that becomes your answer, okay? So we have multiple problems here, but there's nothing we cannot fix with typecasting. In other words, for every safety device, or safety feature in C, there's a way to defeat it. And you basically tell the compiler and say, I know what I'm doing, let me do this, okay? And that's exactly what we're doing here. We'll just say, oh, you know what? Treat this as a char pointer. So I'm going to force the interpretation of x, which is an integer, as a char pointer. And I'm going to do the same thing here, okay? Look at the address of the entire record and treat that as a char pointer too. So now I'm fixing two problems with one mechanism, which is typecasting. Because what I'm doing is, first of all, I fix the problem of I'm subtracting pointers of different types because they're both char pointers. And then the second problem is also solved because one char is 1 byte. So the result or the difference of this calculation is going to give me the actual offset in number of bytes, but not in number of integers or number of pointers or number of structures. It's actually in number of bytes, which is what I'm interested in. Are there any questions about this particular line? Before we go any further, let's go ahead and run this program just to make sure that it does work. Okay, so do it, return 0. So the program itself really doesn't do anything useful except to confirm that. Oh, by the way, what do you think the program should print? What is the offset to member x inside a struct x? It should be 0. Okay. I'm not sure whether the C standard, the ISO standard for C, guarantees that an earlier member or a member that is defined earlier must have an early address. Does anyone know about that part? I mean, just because x appears before y, does that imply that y has to have a higher address compared to x? Nobody knows. Okay, it seems to make sense, but there are certain things that the ISO standard does not specify. So if it does not specify, it is possible that the compiler goes in and go, you know what, I'm going to change the order of the address because you're not supposed to rely on the relative addresses between these members. Okay.
So it could be like the when you're passing parameters where it does the last parameter first.
Not quite. That one is enforced. Okay, the C standard, actually, it does not explicitly state that you have to push the last parameter first, but in order to implement a variable number of parameters, that's pretty much the only sane way of doing it. There are crazy ways of doing the same thing, but they're much more difficult to deal with. All right, so we'll go ahead and just compile and run this program. So I'm not going to go through the makefile just to do this part. And then run the program. It prints 0, just as expected. Okay, nothing too exciting here. And then I can do the same thing to all the different members of X. Okay, so I can now say, what is the displacement or offset to member Y, member A, and then I can just change over here, Y and A. Recompile the program and then just rerun it. And it says, the offset to member X is 0, the offset to member Y is 4, the offset to member A, which is the array, is 8. It seems to make sense, right? Because X is an int, 32-bit, Y is an int, 32-bit. So by the time you get to A, it should be an offset of 8 bytes. Okay. Very good. And the last one I want to print, is kind of simple too. I can just say, the size of a struct X is, and in C there's an operator to do it. The size of operator. The size of is actually an operator would actually figure out the size of a particular structure or variable. So you can either pass it the type struct X, or you can pass it the variable var1 in this case. Either one would work. Okay. It should not be very surprising. What do you think should be the output of this program? What is the size of a struct X? 28. So 28 bytes. It's not 29 because when you allocate for an array of chars, the null terminator is already in whatever you're allocating, so there's no extra byte for that. Okay, there you go. Okay, very typical, things that we already know how to deal with. Okay, so now we'll go ahead and write a very simple subroutine to do something. Okay, and then we'll turn that subroutine into assembly. Okay, so that's the trick, is how do we do this in half in C and half in assembly. So I'll just do a void subroutine here, init variable X. We'll take 2 parameters. We'll take I and j as parameters. We also need a pointer to the structure, the one that whatever we are initializing. So we have struct X, a pointer to struct X. We'll just call it px here. Pointer to X, and we can now say px member I gets member X gets I plus j. This is really just a random example of things that you can do with a structure. And then we can also say p points to A bracket 0 gets t, and then we give it a null terminator right after that. Are there any questions about the subroutine itself, in C? Okay, we're not worried about the assembly implementation at this point. We're just looking at the C code. Are there any questions about what init X is going to do to the structure? Okay, no questions. Okay, all right. So nothing really important here, and I can test this code, by using GDB. GDB is really useful for this sort of thing. So I can just call init X and give it the address of var1 in this case, and then give it 2 constants. Okay, I don't care. 2 fine, whatever. There we go. But this time when I do the GCC, I have to supply -g to include debug information, and then we can use GDB to debug the program, because this time I'm going to have to use a breakpoint to show that the structure is actually initialized. So list the program, put a breakpoint on line 25 after init X, run the program at full speed. Now it is right before the return after init X is done. Then we can just say print var1. Because GDB can read the definition files from a C file, it actually understands how to parse a particular structure. So in this case, it knows that a structure X, struct X, has a member called X, and this time it has a value of 7, which makes sense. Okay, it's 3 parameters that pass to it, 2 and 5. So 2 plus 5 is 7, 2 minus 5 is -3, and then when you look at array A, it does start with an uppercase T, a null terminator, and then the rest is gibberish because it's not initialized. Okay, so everything is working kind of as expected. There's no surprises here whatsoever. Okay, still doing okay so far with this code. Okay. So now I want to implement init X in assembly. Okay, So this is the core of this class. Okay, there is how do we look at a subroutine like what we have here in X, and then implement the entire thing in assembly language. So that will be the first challenge. It's just to get it done first. Okay. So we'll go through different phases in this class, in this particular session. So the first one is to implement init-x in assembly. And the way we'll do it is to look at struct1 first, copy and paste a bunch of lines, comment out this part, but keep the header, the prototype, because the C compiler still wants to know how to pass parameters to init-x, so I have to keep the prototype. The definition of the subroutine is now gone because I want to do it in assembly. Then I'm going to take a look at this, starting on line 10 to this line here, 10 to the current line, yank, switch back to the assembly language file, and now I want to do everything in assembly. Substitute the beginning of each line with pound, okay, because the first pound is not safe, 1 pound is not safe because pound if, will be interpreted by the preprocessor as a pound if, but if you have 2 pounds, then it's safe. Okay, so now we have the commented out code in C. Start with a .text section. Give it a label init-x. That's the entry point of the subroutine, and this is the exit point of the subroutine. All right, so we have our usual stuff, trying to figure out the offset to each individual parameter, and that part we should know pretty much, by now. So we'll go ahead and start. I always start with old EBP. You don't have to, but it's really a force of habit for me to always start with old EBP. Return address is old EBP plus 4, and then the first parameter px is return address plus 4, and then I is px plus 4 because an address also takes up 4 bytes, and then j is I plus 4 because those are 4-byte integers. I should have used int32_t to really emphasize that these are 4-byte integers, but for the time being, I'm just going to do it kind of in a sloppy way. Okay. Are there any questions about the calculation of displacement to the individual parameters in this particular subroutine? No questions about that? Okay, so we are ready to move on. All right, so the next thing we have to do is to deal with the entry point code, which is always push EBP, move ESP to EBP, and then the exit code will be kind of the reverse of that. We have move L, EBP back to ESP, pop L, EBP, like that. So if I do it this way, I will not forget, I will not do one but forget the other one. Okay, either I forget both, or I will remember both. All right, so that's not a big problem. Okay, this is the first statement that we want to translate. We want to put the sum of I and j into member x of px. Well, before I do anything of this sort, let me define a whole bunch of other symbols to represent the displacement or the offset of each member in the structure from the beginning of the structure itself. Okay, so that's the first thing I would do, is to define another bunch of symbols, either at the beginning or at the end. It doesn't matter where it is. So in this case, you know what? I'm going to do this part too. I will have a header file. So I'm going to have a header file called, I just call it struct_x.h, because it is going to define struct_h, but in assembly. So instead of using .h, which is implying is a header file for C, I'm just going to use inc or include as an extension for include files in assembly. So this way I can look at the extension of a file and know instantly, is it intended for C or is it intended for assembly language. Are we still doing okay so far? It's really just a convention of mine in this case. You can call it .include, spell out include, it doesn't really matter as long as you use it consistently. Okay. So I go into this file, and these are still assembly directives. So I can say x, uppercase x, underscore, lowercase x, and I'm just using this convention to define, this is the offset of member x in a struct x. That's the intention of this particular definition. According to the program earlier, we know this is 0. and the offset to y or member y is 4. The offset to member A is 8. And then the size of the entire thing is 28. You don't have to do it consistently like this. You can use your own convention, but I just pick a particular convention, so when I look at a symbol like this, I know instantly what it means. This is basically how you define the structure in assembly programming. Okay? You don't define it like a real struct. You just use individual labels, and I just use a particular structure for the name itself, for the label, so it's clear what I'm talking about. Are there any questions at this point? So these are just regular label definitions, much like the other ones in the other file. So now we can switch back to the other file in initx.s, and now we can do a pound include, and we're going to include struct x.inc. Just like in the C file, you can do a pound include something.h that you create. Are we still doing okay? All right. Now that we have those definitions, which are really just symbolic definitions, how do we do something like this? Well, let's deal with the right-hand side first. The right-hand side, for the right-hand side, we'll just move this into register EAX, and then we add J to EAX, and I'll just push it on the stack. In other words, whatever the result is, we just push it on the stack. And now I want to calculate where am I supposed to store this. Okay. What do you think? How am I going to implement px points to x in assembly? And I don't want the value of member x of whatever px points to. I want the address of that, so I can store into it.
The same way you'd access any other local variable?
Okay, so we'll use px first. Okay. And I can safely put it into EAX because the value, the sum, is already stored on the stack, so I can reuse EAX for this purpose. At this point, right after this instruction, what do you think is in EAX at this point? We just copy the parameter px to EAX. What is px? Do you remember from the C code? What is the type of px?
It's the address.
Is an address of a struct x. Okay, very good. So let's comment it accordingly. We'll just say, EAX is a pointer to a struct x. Okay, not really surprising because that really is the type of px itself. Now, I claim that I'm ready to store the sum directly into where it's supposed to go in one single instruction. Now, because the result on the right-hand side is already pushed on the stack, if I say I can do this in one single instruction, it kind of implies a pop instruction. Okay, so we'll handle that part first. Okay, we are popping the result from the stack into its final destination. But how do I specify the final destination now that EAX is PX?
Direct.
Direct. You want indirect. Now in this case, a simple indirect would work, but you want to make it a based, just in case I move x around. Okay. So the proper way, or one way to do it, I wouldn't say this is the only way to do it, but one way to do it is just like that. Because EAX is pointing to the beginning of the structure, and then x underscore x is the displacement from the beginning of the structure to member x, lowercase x, in that structure. So this is exactly telling me where I'm supposed to store into member x of whatever EAX points to. Okay. Are there any questions about this? Yep.
How is it reading x underscore x? It's not on this file.
It is in the instruct x.inc, include file will define. Okay. So once we are done with this one, the other ones should be fairly simple to deal with too. And so the next one is about the same thing, except it's a subtraction instead of an addition. So if I'm lazy, I would just do a copy and paste here, and then change one of the instructions. So since I put I into EAX and it's supposed to subtract J from it, so that's really easy. Just turn the add into a subtraction, and then turn X to Y. So now I'm storing into member Y of a struct X instead of member X. Are we still doing okay so far? Yep. Go ahead.
How do you copy one code sequence?
You go to the first line that you're copying from, and then you use 5. You type 5 on the keyboard, which means I want to perform this operation 5 times, and then you do 5 YY for yank. So you're yanking or copying 5 lines into the clipboard, so to speak. And then you move to the paste point, here, which is the line before where you want the new content to appear, and then you press lowercase p to paste. Those are all VI commands. No, it is not in any particular section because it really doesn't matter because all you're doing is you're defining symbols. And symbol definitions can go anywhere because there are no .int or .byte type of application. So it doesn't matter which section you're in because you're really just defining the literal values of the labels.
So we could put it in .text if we wanted.
You can do a pound include at the end of this code, it doesn't matter. Because the assembler doesn't care about the order of definitions. In other words, if you use a label before it is defined, or you define a label before you use it, it doesn't care. Right. So now we are ready to move on to the last 2 instructions. These 2 here, we can do pretty much the same thing. We can just say move PX EBP to EAX. It's already there. So if you don't want to do it this way and just keep EAX, already, which is already there, you can do this one in one single instruction, which is a move B, and then you're moving immediate the uppercase T ASCII code to. Okay, where am I going to copy it to? This is the first byte in the array A. The array A or member A is this many bytes away from the beginning. And this is the first byte, which is 0 byte from the beginning of the array. And EAX is already pointing to the beginning of the structure, so this will get it done. Now I know the plus 0 seems really silly, but I want to put it there because the 0 is corresponding to the index of the square bracket or the index operator. And that's why the 0 is not really silly because I want to emphasize that this is the actual index into the array. Because when you look at the next one, then you just put a 1 in place of the 0, and then the ASCII code 0, or the ASCII code of the null byte is just 0 itself. And I'm done. Okay, this is already done. Are there any questions about this subroutine? No questions? Okay. If there are no questions about this, we'll go ahead and run it and see what happens. Okay, just to make sure that this is still working the way it's supposed to. So gcc-g to include debug information, -o to specify the executable name, which will still call struct1. Then we will supply the source files. Struct1 is 1, and then initx.uppercase s is the other one. And it's complaining undefined reference to initx. Okay. That's because when I defined this, I forgot to do one thing, which is .global initx to export the label initx to the linker. Because otherwise, all label definitions stay within the file, and the linker doesn't get to see it.
Should we include the after .text, or is it?
Doesn't matter. It doesn't really matter because those are really just simple definitions. So as long as they're just simple definitions where you start with a label name equals and then whatever number you want it to become, it doesn't matter where you put it. The time when it is important is when you have a label name colon, and then you define the .int 0 or .ASCII something. Then it depends on whether you plan to change those bytes or not. If you plan to change those bytes, they have to go into .data. If you do not plan to change those bytes because they can stay in .text. All right, so now that we fixed this little problem, I think we should be able to create the executable, and then just like last time, we'll use GDB to look at the effect of the subroutine. And the same thing, we'll put a breakpoint right after initx is called onto line 28, run the program, and then print var1, which is our structure, and it works exactly the same way as before. Are there any questions at this point? No questions?
When you
So
list-
now, go
When
ahead.
you listed your program, did it also list the assembly in there?
Assembly code?
Yeah, I didn't see. So it wasn't listing the contents of the subroutine.
Oh, you want to list the content of initx?
Yeah, like you want to add a breakpoint in that particular portion.
Sure,
of the
you can do that.
program.
I mean, you just have to say, if you want to set the breakpoint, you say B. But if I want to just list the content, it's L and then the file name, and then you give it a line number to begin with. And that way you can, you have access to your assembly code as well.
So it would be the same thing. B, the file name, and then the.
And then the line number after the colon. Yep. Yep. So now you can actually debug a program that's partially written in C and partially written in assembly. Okay. All right. So now that this part is done, we'll go ahead and clean up struct1 a little bit. Because the way struct1 is written right now is not very portable, because the definition of struct x is actually inside the .c file. I'll move that out into its own .h file. So we'll go ahead and let's see, 1, 2, 3, 4, 5. So 5 yank, create struct x dot uppercase lowercase h this time for C include file, just like that. Now there are tricks about how you create a header file, because sometimes you have to avoid having the same include file included twice. Okay, that's because an include file, one .h file, can pound include another .h file, and many times if you pound include a file, the content twice, it won't work, because if you pound include and try to parse this definition twice, the second definition will fail, because the compiler will say, oh, struct x is already defined. You cannot redefine something that is already defined. So there's a trick to do this. I'm not sure whether your C class talked about this. So what you do is you say, if not defined, and then you create a name of a macro that is related to the name of the file itself. So in this case, it is struct x underscore h. Okay. I think that's a standard to do it, but I cannot remember what the standard is. So I'm just going to go with a very simple one here. So once you have these lines included, then it is impossible to try to define struct x twice. Because what this is saying, okay, if struct x underscore h as a macro is not defined, then go ahead and do everything that is specified all the way until the pound end if. So that includes two things. One is the struct x definition itself, and also the definition of the macro struct x underscore h. So the second time you include this header file, it will look at, it will go through the first line first, the pound if not defined struct x underscore h. But the second time it will fail because it's already defined. Then it will skip around the entire content, and then we'll just skip all the way to pound and if, which is already at the end of the file. So you won't have a problem pound including the same file twice or as many times as you want. So it's a little trick that I picked up, in projects that I do, stuff like that. And getting back to this program, now I have to say pound include struct x dot h, and now I do not need this part here, just to recompile the program to make sure I didn't break anything. Okay, it's all good. All right. Are there any questions about this particular program at this point? Very typical use of the definition of a structure, putting into its own .h file. The only part that is kind of weird is, oh, we can also access that structure in assembly. but we can do it because we print all the offsets to different members of a structure. So in assembly, we can just say, oh, we know how to find the member. If you tell me where the structure is, I know how to access each member that I need to access. No problem. Are there any questions at this point? So what I'll do next is I'm going to mess up this program. And it's not something that you would normally do intentionally to break a program, but nonetheless, it does have the effect of causing problems. So what I'll do is I'm going to change this definition here, and we'll just go ahead and rearrange things a little bit here. So instead of putting A as the last member, I'm going to change the order just a little bit like that. Okay. That is not a big change. I mean, I'm just reordering various parts within the structure. You look at the C code. Do you think that change would impact the C code at all? In other words, do I have to change anything here to accommodate for that change? Nothing, right? Because I'm not relying on the relative ordering of the members of a particular structure. I'm not changing the type of the members either. X is still a 32-bit integer, Y is still a 32-bit integer, and A is still a 20-byte array. So this code should work just fine. What about the assembly language code? That's toast, right? It is toast because struct x dot uppercase s. Oops, how did I call that? Oh, struct x dot include. This is decoupled from the .h file. In other words, I changed the .h file. This doesn't get updated right away. I have to manually go in and say, oh, you know what? A is now the first member, so I have to change x underscore A to 0. X underscore X is going to be 20, and then X underscore Y is going to be 24. I have to go in and make that change manually. But every time you have to do something like that manually, it's not good news, okay? Because you have to do it manually. All right, so we have to fix this problem somehow. How do you think we're going to fix this problem? Yep.
Well, I was wondering, what if we use the template instead of a struct?
Sorry?
What if we use the template instead of a struct?
A template is sort of a struct, like a C++ template.
Yeah.
Oh, we're not going to go there. We're not going to go, where templates or even classes are, because the classes have inheritance, right? So if you have a class that is a subclass of something else, then you would have to figure out the displacements to the members, not only of the class itself, but also the displacement to the members that you inherit from the superclass. So it causes a lot of interesting issues. And then with classes, you can also potentially have member methods. You can have methods associated with the class. So then you have to get into the whole thing about, okay, how do we name those methods? Because it is possible we can call a method that belongs to a particular class definition. The only part that is kind of tricky is self, which is the pointer to the object itself, is actually a parameter. But you don't see that in C++ because it's implied. But when you do it in assembly, you have to push the address of the object itself, and then you call the subject. Okay. But that's we're not going to touch that. We'll stick with just basic good old C structures for now. All right. So what we'll do now is I'm going to borrow a makefile from the previous class. So I'm going to do a CP 2013-0430. And oh, I did not even have a makefile on that day. Okay, we'll just borrow that one. And we'll just adapt this makefile to this particular project. So the C code will consist of struct1.c, and then the assembly file is just going to be initx. And we're not going to deal with the C executable, so let's get rid of that. Okay, now it's interesting because we have an include generation executable. That's what it is. Okay, it's an executable to generate the include file that we can use in the assembly source code. So I'm going to give you the name. We'll just call that struct x gen. Okay, for struct x include struct x include file generator. Okay, it's really just a name. Doesn't matter. Okay. And we have to keep that name in mind because the .c file has to be the same thing. Has to be based on the same name. And then the include file has to be consistent here. So it's struct x .inc. And we'll keep this name the same way as the other one. So this is going to be incgendexe dot all right, I'm going to explain everything here. All right, the first thing is this entry. Let me turn on the line number. On line 9, okay, line 9 is really just a kind of like a table definition, except this is inside the big file. So I'm just equating, uppercase incgendexe to a file in this case. So that next time I want to make some changes, I don't have to change the rules. I just have to change the definition of the labels. Okay? So that part is relatively easy to explain. Then we have line 14. Line 14 is basically saying, in order to create the executable, look for a .c file, of that same name. But the dependency is the executable depends on the object file. So I'm looking for .c file, and then we change the source code name to .o. So I'm forgetting one definition here, which is the name of the source, which I have to define up here. There we go. Struct x inc gen.c. So I'm forgetting that particular entry. So line 14 is basically saying, how do I create the executable? Look for the source code name, but change the file extension from .c to .o. Yep.
So is that written with like assembly syntax?
This one here? No, this is all make file syntax. So I'm still specifying rules in the make file. Now what is kind of interesting is line 16. Line 16 says the target, which is struct x.inc, depends on the executable, which is defined by the name of incgendexe, include generation executable. And in order, so that means every time I update the executable, the include generation executable file, it knows that it has to regenerate struct x.inc. And in order to regenerate struct x.inc, it will run the command on line 17. So it will just run that program, capture the output of that program into struct x.inc. Are we still doing okay so far? Okay. So if you look any further, this is a little bit different from. Yeah, this is one of those kind of really funky type of program. Okay, so what we'll do next is to write the actual code for the include file generation program. And that will be called struct x include file generation. And this is a .c file. And we'll do a include stdio.h. And then I'll cheat a little bit and copy some code from the other program. So I'll copy from struct1.c, and particularly I'll copy these 4 lines. Oh,
Those 2 lines.
yeah. All right, but nothing we cannot fix easily. But the output, instead of making it like this, guess how I'm going to change it? turns out copying all those lines may not be that helpful anyway because I have to change all the keys. That's it. There we go. That's the content of this program, which is almost the same as struct1.c, except the output of this program is suitable as the include file. Is that okay so far? So there's no special logic in this program. The only thing special is the output format. It is no longer intended for a human being to read. Instead, it is now compliant to the assembly language of the assembler, so it can be generated or be considered as an include file. Yep.
Struct X. I don't know what the struct X is.
I'm forgetting the pound include struct x dot h, which is also important. Yep, here we go. Pound include struct x dot h. Yep, you're right. Forgetting that file, because otherwise the definition of struct x is not in this particular program. All right. So are there any questions about this particular program? Okay. Let's go ahead and make it, and just to make sure that I didn't make any stupid mistake in terms of syntax and stuff like that. So we'll go ahead and make struct x include generation, and it knows how to do it. In fact, it goes through all the rules to actually regenerate struct x.inc already. So you look at struct x.inc, which is the include file for assembly language. It's all updated. So this is really kind of cool because now if I say make struct1, I'm not sure whether I updated that part or not. Now, what did I do? Executable is okay. It's not main. Struct1. Okay. Let's go ahead and make clean first. Okay. Make sure that we're using a clean slate here. Make clean should also clean up struct x.inc because it is actually now generated. So what we'll do is we'll go ahead and make a little change to struct x, the definition of struct x, but in the header file here. I'm going to put something in front of everything, therefore changing the displacement to everything, right? So we'll just put another char array here, char b. It has 8 bytes, okay? And then we'll do a make struct1, and we'll see what's going to happen. Okay, if you look at the output of make, okay, I'll just highlight the portions here. The first 3 lines, are basically saying, okay, those dependency files are not there. So in the make file itself, when I'm trying to include those dependency files, they're nowhere to be found, and the make these are warnings. It's not fatal errors, because it will generate these files using the following commands. So when you look at the next 3, commands, this is one single command. This is another command down here, and this is another command down here. These 3 commands will regenerate the .d files. Each of the .d file is a dependency file, just basically specify, in order to create this object file, you would need these source files. In order to create these object files, you would need these source files. And once those are generated, then the make file can now read those dependency files, and then it knows the dependency of everything, including the first thing it has to do is to recreate the executable that eventually will create the executable that will create the include file for the assembly version. And this one is just recreating the .o file, the object file. and then the next one will do the linking to create the executable. So at this point, we have the executable to create the header file from the assembly programming perspective. And that's what it's going to do next. So the next step is to recreate the assembly include file. Once we have the assembly include file, the rest is really just the usual thing. This is the C code compiling into the object code, compiling or assembling the assembly code, and then we can link the two to the actual executable. So everything is quote-unquote automated. But what about that new member B in struct X? We don't have that definition in the assembly code.
It's not needed.
It's not needed because I have no references to X_B. Now, if I do, then I have to go back and change the C file that generates the include file for assembly to include that entry. But as long as I'm not adding any new entries, I can make all the changes that I want, and this will automatically take care of everything. Well, maybe you're not convinced. Well, if you're not convinced, let's go to .h here, and this time we'll just shuffle things around yet again, okay? So I'm making a trivial change in the definition of struct X that is not going to impact the C code whatsoever, because the C code has the C compiler to take care of this. But the assembler does not have any direct linkage except for the make file. So when I say make struct 1, which is the final product that I want, it triggers all these operations. It triggers the operation like this one first because it realized that initx.s has a pound include to include struct x.inc. So this is the first thing that gets triggered, is to recreate the dependency file for initx.d, just in case inside struct x.inc I add another pound include. This will take care of the recursive include. The second file that gets regenerated is this one. Because I just changed struct x.h, which is the header file, to the C program. So every C program that depends on the header file, they all need to be recompiled. And this is one of those .c file that has to be recompiled because it has a pound include struct x.h. So that makes sense. And then we have our main program, which is called struct1. Struct1.c also has a pound include struct x.h, and therefore it has to be, the dependency has to be regenerated because just in case I have another embedded pound include inside struct x.h, that has to be recompiled just to make sure. And then you can see this part here. Oh, it does not. Oh, okay. Did I miss some part? Yes, I did. I missed this part here. It regenerated the executable for the header file the include file generator is recompiled first, and then it is regenerating the include file for the assembly, and then trigger the rest of the operations. In other words, it does take care of everything, quote unquote, automatically. Is that okay so far? Just a general idea, not really the syntax so much or the actual commands, but the general concept of how I can use a program that I write myself and some tricks in the make file. I can now make sure that my assembly version or the assembly code that depends on the structure to be fully synchronized with the C definition of the structure. Is that okay? All right. Wow, that didn't take as long as I thought it would take. So now we can debug struct1 just to make sure that everything still works, right? I mean it can assemble and compile and link, but it may not work. So we got to make sure that it does work in the end.
We're relying on a C crutch.
A C crutch.
This isn't pure assembly. This is a melding of C and assembly.
This is a melding between C and assembly. That's right. So run the program up to this point, and then we'll go ahead and print var1, and it still has 7 in X, -3 in Y, and array A still has uppercase T, and then a null terminator. So the program does work, as expected. B is not touched, so it is still initialized. All right. So, any questions before we go any further? No questions? This is all good?
Yeah, if you were essentially wanting to create a structure in assembly, you're just paying attention to where you're storing things in memory. You're not actually defining it like you do in C.
I'm not defining in C. So the source is still in the C definition of the structure, but the definition in assembly is going to mirror that. So as soon as I change the C definition of the structure, the assembly version will get updated, which will trigger the .s file to be reassembled.
Not what I was meaning. I was meaning, like, let's say, he was talking about how this is the melding pot and it's not
Mhm.
pure assembly. If you wanted to write just a pure assembly programs that they use a structure, it's going to be up to you to remember what you've got in what order.
What you could do is you could do based offset for defining the offsets and put it in the data instead of using the scheme we did for like the last stuff. You could
But even if you do it in pure assembly, I would still do the structure in C, just so that you won't miscalculate the offsets.
Well, couldn't you define the offsets in a .data section and have them, or define like the start of each? You have an offset.
Each member?
Yeah, that's the start of each member defined in the data section that can be changed, and then
You
everything
could
else
do
is an
that.
offset from that. Like,
Yeah, you
it's always
can
a
do
function
that.
offset.
Yeah, but if you do it in C, then you have the assurance that the offsets and the types will be done correctly. So I would still do as much as I can in the C definition, and not in assembly. But that's just my personal preference. Okay, the next question is, why would we care about something like this? What will be the rare chances that you want to mix, C code with assembly code, and they have to understand the same structure? Why would we even care about something like that?
You don't like the compiler's choices.
Or you write in a real-time kernel. Okay, you can write a real-time kernel. Why do we want to? What is a real-time kernel? Can anyone know? Does anyone know what a real-time kernel is, and kind of briefly explain what it is? Nobody knows. Okay, a real-time kernel is a kernel, which means it's the core part of an operating system. But in this case, as a real-time kernel, its main job or the main property of a real-time kernel is for scheduling, for real-time stuff. In other words, you will be able to use multi-threading, and then you can say a thread can basically say, okay, I want to suspend execution for now for X many ticks or X many milliseconds, whatever you want to measure the time. Okay, and then X many milliseconds later, the kernel will be responsible to basically resume execution of this particular thread and say, oh, okay, you have waited enough time, it's time for you to get started again. That's one function of a real-time kernel. Another function of a real-time kernel is to support multi-threading, okay? In a very simple sense, okay? So we are not talking about the Linux kernel, we're talking about, oh, I just want to have multiple threads in the program. So this function written in C has its own thread, and this function written in C has its own thread, so they can execute in parallel at the same time. Okay, so that's also another responsibility of a real-time kernel, is to support multiple threading, but in a very minimal sense. Okay, we're not talking about file systems and all the complicated stuff. We just want to be able to do parallel processing. A real-time kernel can also have priority queues. In other words, certain things are more important, they have a higher priority, and other things are less important and they have a lower priority. So if you think about the robotic application, the subroutine that deals with user interaction, to report its temperature through Bluetooth to your cell phone, has a lower priority, because if it's late by 50 milliseconds, nobody's going to notice anything. On the other hand, the motor control logic has to run as a high priority, because measuring the speed and making sure your motor control function is working correctly has a much higher priority, because milliseconds can mean a lot to a particular type of motor. So a real-time kernel can now implement what we call a priority queue, which means you can put certain threads as a higher priority and other threads as a lower priority. The low priority threads do not get any execution time when there is any high priority threads who still need execution time. So that's called a priority queue, which typically it is in Linux too. Okay, this is in Linux. It's called the nice number, NICE nice number. So you can put a nice number. The higher the nice number, the lower the priority. So you can have heavy duty jobs with a nice high nice number. So it doesn't bog down other things that you have to do in the same system. So it would just be using the leftover processing time and not slow down everything else. Yeah, go ahead.
So how does C help you with creating a real-time kernel?
That's a good question. It does not. It does not. So this is obviously out of the context of this class. It won't be in the final exam. But this is the kind of stuff that I really like to do myself. So I'm just going to go to my website, go to develops, and then go to real-time kernel. And this is a little real-time kernel that I wrote in one summer. Okay. So yes, I can write an entire real-time kernel in assembly. Okay, this whole thing has no C code whatsoever. But who's going to use it? How do you use a real-time kernel when it is written entirely in assembly? So whatever program that needs to use it has to be written entirely in assembly too. And that makes no sense whatsoever, right? The real-time kernel has to be written in assembly because you cannot just call and return. Okay, you have to do other things that are very specific to the hardware. I'm going to push all the registers to save the state of a thread. Then I'll manually change the stack pointer when I'm resuming another thread and restore the registers and things that I cannot do in C. Okay, and that's why a real-time kernel, almost has to be written mostly in assembly, if not entirely in assembly. But this won't be useful unless a regular C program can also make use of the real-time kernel. And that's where the interface between C and assembly, subroutines become important, because you might be writing, subroutines entirely in assembly, but you still have to make sure that it is interfaceable from the C perspective, so that your code can be used by a C program. And that's basically what this is. You can go here and take a look at the stuff here, but the program or the kernel itself is written entirely in assembly, but it does have a C API. In other words, it has a C application programming interface. So this way, I have usual pound include files for C programs to make use of the real-time kernel. So this is a practical use of interfacing C code with pure assembly code. Any questions about this? No questions? Okay. So for those of you who are interested in real-time kernel and how it can be useful in robotics, you feel free to read all this stuff here. But otherwise, I'm not going to spend too much time here. So all of these structures, okay, in the API, struct thread is a C definition, but it has a matching definition in assembly, so the real-time kernel knows how to access a particular structure like that in order to do the multi-threading. And the same thing with all the other ones, which is a queue, a tick. Basically a tick is just a 6-byte thing to maintain the quote-unquote time of the system, and so on. So but these are all basically C prototypes. Okay, so you use a C prototype to call a subroutine, but the subroutine itself is written entirely in assembly. And this real-time kernel is 2 kilobyte large. It takes up 2 kilobytes. Like
That's a lot. That's a lot.
when your device, when the microcontroller device only has 8 kilobytes of code space, that's 1/4 of the entire system already. So it is a lot of space depending on the device that you are using. And by the way, this also can be used with the Arduino, because the Arduino uses the AVR processor, and this code, this entire real-time kernel is written for the AVR, family of processors. Are there any questions? Any questions? Nobody's interested in real-time kernel?
If you make the real-time kernel like the whole entire Linux kernel in assembly, it'll be like completely unmaintainable and then the statement like when your computer be like ridiculously fast.
Are you asking why I'm doing it all in
Oh, well, I was wondering if like because I know Linux kernel written in C and I think
The Linux kernel contains portions that are written in assembly because you cannot avoid the assembly code portion. Because in C you cannot control, oh, I want to push all the registers. Well, C has no statements to say that. Or I want to pop all the registers, from the stack. There's no statement to do that either. Or I want to manually move the stack pointer because when you go from one thread to another thread, you have to move the stack pointer. And in C, you don't have direct access to the stack pointer. So you have to write certain portions of the kernel in pure assembly, but you want to minimize that portion so that your operating system is as portable as possible.
Well, I was wondering like what happens if you went that way around and like wrote it all in assembly?
Then it becomes very brittle, which means it will be very difficult to port it to another architecture. In this case, it's okay because it would work with an entire family of MCUs, and I had no intention to port it to any other architecture at the time, and I do not even today have any intention to port it. It's really a little real-time kernel for my own use, because I have projects that I have to do that requires multi-threading and all the other stuff of a real-time kernel. So this is really written for myself. But at the time, I was also teaching micro mouse design at UC Davis. So many of my students, can also use this, on their robots, so they can schedule, tasks, for sensors, for motors, for user interaction, and path planning and stuff like that. So it turned out to be kind of useful for that purpose too, but it was not really intended to be a general purpose, operating system. All right. Are there any questions? No questions. The source code of this, actually can be downloaded. I do want to kind of go over maybe one sample program. This is a sample program to use the real-time kernel. It's completely in C. So RTK initialize or real-time kernel initialize itself is written entirely in assembly, but you can call that from C. So it's basically doing exactly what we are doing in this class. We have pure assembly language, subroutines, and it can be called from C. And the C compiler just needs a prototype and the entry point. The rest, it doesn't care. Yep.
Was C designed in mind to interface with assembly?
Yes. The origin of C, Carnegie and Ritchie, those were the two people working for Bell Labs at the time. And Bell Labs belonged to AT&T, and that's the organization who started Unix to begin with. So these two guys were writing the operating system Unix, all in assembly initially. And then at some point, they just got bored because they're writing an entire operating system in assembly. And I'm not talking about a real-time kernel. I'm talking about a fairly sophisticated operating system with file systems and all the other stuff. It can be a chore. It's not really exactly a good use of time. So they invented BCPL, which is the predecessor of C, as quote-unquote more like a macro language. So they can specify commonly used operations using a high-level syntax, a shorthand, so to speak. But it was really just an agreement, a tool to help themselves to write an operating system more effectively, so they don't have to write everything actually spelled out in assembly code. They can just use quote-unquote macros to say, oh, okay, this macro will implement a variable, this macro will do certain things, and that, and so on and so forth. So it wasn't really quite the same as a modern programming language. In fact, type checking was added much later, compared to BCPL, because these guys knew what they were doing. They had no need of actual type checking. But the language eventually evolved into what we know as the C programming language, and that was in the 70s. I think the C programming language was first released to the public in the 70s. And then after that, people added all kinds of features to it, including all kinds of type checking, and even with parameters, the way we specify parameters, like it's not shown here, but the way we specify parameters in a prototype or a header of a subroutine is not how it was done originally. Originally it was specified in a completely different way, which is by today's standard, I think it's not only deprecated, modern compilers won't take it anymore unless you use a flag to say, okay, be more backward compatible than it can take the code that was written long ago. So C was never intended as an instructional programming language, and that's why it's so tricky to use. With all the confusion between pointers and arrays, it's not coincidental. It's not by design to be confusing. It's basically in assembly programming, a pointer is a pointer, and you can treat any pointer as an array or as a pointer by itself. It doesn't make any distinction between a pointer and an array. And that's basically from the language itself, from the origin or the heritage of the programming language itself. So C was intended as a low-level programming language, just one little step on top of assembly language programming. And that's why it is so easy to specify code or there's a standard to interface assembly code to C code and back. So that's a good question. It's just a
It's almost an accidental language.
It was a tool. It was basically a tool written by experienced programmers for themselves. It was never intended as a instructional programming language by Haskell. But at some point, universities started to convert to C as the de facto standard of programming languages, and that's why we are now using C as an instructional programming language. But it was never intended as such. All right. Okay, one more thing. We got 3 more minutes to go. Do you guys still remember the swap subroutine? Okay. So if I want to do a swap subroutine here, okay, so the swap subroutine itself is pretty easy to implement. So we have PA and PB. It's T. Okay, we have T gets whatever A points to, whatever A points to gets whatever B points to, and then whatever B points to gets whatever A was pointing at earlier that we saved earlier. Okay, so that's the swap subroutine. Nothing really fancy, it's pretty easy to do. Okay, now how do I do this? How do I swap member X of whatever PX points to with whatever with member Y of whatever PX points to? I'm not passing X as a parameter. I'm passing the address of X as a parameter. So I will leave this one as kind of like a brain teaser for you guys, so you can try to figure this out, and then I'll talk about it on Tuesday. We already have everything that we need to get this done. It's just how do you put all the pieces together to implement this one call to swap. If you know how to get to the content of a member, you know how to calculate the address. So the bottom line is we know how to do it with one single operand, but how do we calculate the actual address using the other instructions? That's really the question. Okay. All right, so we are running out of time today. I'm still grading the exam, so I'm not forgetting it. I'm still grading it. And then over the weekend, I should be finished with that and also some of the homework assignments. So on Tuesday, we'll talk about this, and a new homework assignment will be available on Tuesday. Maybe the last one that we are funding.
Will it be doable?
We'll do binary search tree examples.
I remember the binary search tree. We failed deleting it, I think.
Everybody failed.